Damn, it feels good to be a gangster.
For the first part of the lab, we had to calibrate the axometrics. In order to do this, we had to keep the red arrow centered on the green portion of this. If it went to the right, it means there was too much gain, and if it went to the left portion, it means there wasn't enough light getting through the system. We had to redo this for each wavelength filter. Yes. Shut the fuck up, bro.
We're recording. We're recording.
The next, we close this tab and open up this one. Right here on the right is the Poincare sphere, and this gives the orientation of the polarization. All we did was we changed the voltage for each reading, hit run once, and recorded these values. For this part of the lab, we had a laser, 2 linear polarizers, detector, and a LCC. Without the LCC, you have 2 linear polarizers that are oriented at 45 degrees from one another, so you theoretically should get 0 light coming through. However, when you place the LCC through, you end up getting a sinusoidal wave as the LCC changes the polarization state, which changes the intensity hitting the detector.
The polarization of light. As we know, light acts as an electromagnetic wave, where the electric and magnetic wave sets oscillate orthogonally to each other. The orientation of the electric wave is the orientation that we're interested in for the polarization of light. As we can see here, the electric wave oscillates in a plane. Here, the electric wave oscillates in a circular polarization with regards to time, and here it oscillates in elliptical orientation with respect to time. How do we polarize light? There are 3 elements that can alter the polarization of light. One is polarizers, which directly attenuate incoming polarization of the beam. And diattenuation relates to how good the polarizer is by determining determining the orthogonal polarization state transmissions. Retarders are used to create a phase delay from input to output, and depolarizers scramble incoming polarized light. The Poincare sphere can be used to describe all polarization states of light, where the equator has linear polarized light, and the poles have circularly polarized light, and everything else is elliptically polarized light. Stokes parameters can be used to describe the polarization of light, where S0 is the intensity, S1 is the intensity between linear horizontal and linear vertical polarization, S2 is intensity difference between plus 45 degrees and minus 45 degrees polarization states relative to the x-axis, and S3 is the intensity difference between LCP and RCP. Here are some example Stokes parameters. So the degree of polarization relates to how well a beam is polarized. A DOP of 1 means a completely polarized beam, and a DOP of 0 means a completely not polarized beam. Mueller matrices are a convenient way to represent polarization, diattenuation, and depolarization in one form. They are experimentally found by using a Mueller matrix polarimeter. The setup of a Mueller matrix polarimeter is shown below, where we have a fixed linear polarizer and a rotating linear retarder on the source and detector side. This creates all polarization states possible, and the polarization is analyzed as it passes through the sample. In the experiment, here's the source and here's the detector, and we have a LCC in the middle, and as we varied voltage, we found the retardance of the liquid crystal cell. The liquid crystal cells point along a director, which is the common axis, and nematic liquid crystal cells are where the molecules point in the same direction, and twisted nematic are where the top and bottom are orthogonal to each other. Here's a nematic LCC, and here's a twisted nematic LCC. The construction is the molecules are placed in between the glass layers which hold the form of the molecules. And these are connected to electrodes which can change how the liquid crystal cell affects incoming light. The response, by changing the voltage, you can essentially change the orientation of the molecules, which changes the transmission of the liquid crystal cell. For the second part of the experiment, we placed the liquid crystal cell in between 2 cross polarizers. We did this to attenuate the laser beam by adjusting the voltage, but we were unable to adjust the voltage, so therefore we rotated the LCC, acting as a retarder at 0 voltage.
Here are results for the experiment performed at 535 nanometers. As can be seen, the raw data experiences only a single inflection that can be easily corrected and offsetted appropriately. Here are the results at 660 nanometer wavelength, which shows a little more fluctuation of data, but can also be reasonably corrected and offsetted. Finally, here is the data for transmission of the LCC between 2 cross polarizers. As the LCC rotates, we see an almost perfect sinusoidal transmission pattern cycling exactly 4 periods.